This lecture is going to be about color, which is a really rich subject that could be its whole own class, really. So I'm going to try and compress a lot of things very simply and quickly. I've mentioned a few different times in previous lectures the idea of the RGB or CMYK color space. I'm going to explain what I mean by that now and why you would choose the different ones. So color is created in two different ways. If it's coming from a light, a natural light or an artificial light, so either the sun or like light bulbs and stuff, if it's white light, especially white sunlight, and you run it through a prism, it breaks into the color spectrum, which is like the rainbow or what you would get on the color wheel, so the gradient of the rainbow. So when we were talking about light, color in terms of light, which is what we'll talk about, like a screen is a projected light, then we're talking about additive color, and that deals with the behavior of projected light. This is a bit different than what you're used to. In grade school, they teach you red, blue, yellow are the primary colors. That kind of works when you're painting, but it does not work for us at all. Red, blue, and green are the basic colors in light. If you combine those three all back together, you'll get back to white light. Then the opposites of those when they mix is red and green mix to make yellow, which would seem totally weird if you're used to mixing yellow and blue to get green with paint. But red light and green light mix to make yellow. Blue light and red light mix to make magenta, and blue light and green light mix to make cyan. And then to get black, you just basically take away light. The other way that color works is the light hits something. It's not projected, but it's reflected off of an object. So here we have the red, green, and blue color waves of the light spectrum coming to like a red object. So say it's a red rose. What happens is the red rose absorbs the blue and the green lights and it reflects the red light. So it's actually keeping the blue and the green and getting rid of the red. And then the red wavelengths hit your eye, so you see the object as red. If you've got a green object, it keeps the blue and the red. And if you've got a blue object, it keeps the green and the red. Now, if you see something that's cyan, what's happening is it's keeping the red, but rejecting the green and the blue. If you're getting magenta, it's keeping the green and reflecting off the blue and the red. And if you're seeing yellow, it's keeping the blue and reflecting off the green and the red. So that's what we get, what is called subtractive. And this is a little bit closer, subtractive color is a little bit closer to that red, yellow, blue that you get when they're teaching you how to mix colors in kindergarten, but it's not the same. You'll see that the magenta and the cyan are definitely not the blue and the red that you're used to. So yellow and cyan mix to make green. The cyan and the magenta mix to make what you're standardly used to as seeing blue, and the magenta and the yellow mix to make what you're used to seeing as red. And then if you mix them all together, you get like a muddy brown color. So we have to add black into that, and that's why this is called the cyan, magenta, yellow, CMY, and then K stands for black. So if you're going to work for something that's going to be projected on a screen, you want to make sure the color is set for RBG. That's red, blue, green. You want to work in the RGB color space, red, green, blue color space. And if you're working with things that are going to be printed, you want to be working with the CMYK. So you're printing in cyan, magenta, yellow, and then black to make everything dark. We will still, though, when we're talking about color schemes, still kind of rely on that old red, yellow, blue color wheel. This was developed by a fellow named Johannes Itten in the Art of Color in 1920. So this would be like if you were mixing paint, where yellow and blue mix to make green, yellow and red mix to make orange, and the blue and red mix to make the violet. And that's similar to what's going on with the CMYK. So we get the primary are yellow, red, blue, secondary are orange, violet, and purple. Tertiaries are like yellow, green, yellow, orange, blue, violet. As you mix two colors together, or two colors that are across from each other, on the color wheel, yellow and purple. Those are called complementary colors. They're pairs of opposites, and if you mix them together with paint, they'll move together towards those browner colors. And if you want it to get dark, you would have to put black in it to get it all the way black. Complementary colors, the cool thing about them from a graphic design standpoint is when you put them together, they make themselves look more intense, more saturated. So if I put like the blue next to a cooler color, the blue will look pretty intense still, but if I put it next to the orange, it's going to look really crazy. The orange is going to look oranger and the blue is going to look bluer because the complements are next to each other. There's also a general division in the color wheel, like about right here, between warm colors up here and cool colors down here. That's not an actual like scientific thing, it's just a metaphor. And you can see in this Vincent van Gogh, it's onto the warms, it's orange, yellows, reds, that kind of thing with a little bit of cool in it. And then this Pablo Picasso, you have these very cool colors, all of these blues with a little hint of the warm. So that's another dimension of color we can think about. What I find more useful for thinking about color, though, is a multi-dimensional way of describing color. And that's what's going on in the histogram pickers in Illustrator and Photoshop, any of these. They're thinking three-dimensionally about color. And you have that HSB, hue, saturation, and brightness that you can pick in the color picker as well. That's based off the Munsell color system. So what we think about there is that value is how light or dark a color is, with 10 being white and 0 being black. There's no value, or there's a bunch of value. The chroma, or well, the hue, sorry, the hue is basically just the color wheel. It's the spectrum of colors. So that's the color wheel. It's like on the equator. This is like on the axis of the Earth. And then chroma is in Photoshop called in Illustrator and Adobe, it's called saturation. And that's just how pure the color is. So you know, this like purple blue out here is the fully intense, and then as it moves more towards gray, it gets less chroma, or as we'll say, less saturation in it. So here you can see now we've got more like what we'd see in Photoshop. You have value, or light and dark, running up and down the middle. You have saturation running from the core, and then you have the hue, the color wheel on the side. The hue is a set of pure chroma within a color space, so the pure colors of the rainbow. Saturation or chroma is defined as a range from the pure hue, which is 100%, to 0% at gray. Value is just referencing the lightness or the darkness of the color. White is the lightest value, black is the darkest. If we're talking about grays, the halfway point between these is called mid-gray. And then with any color, whatever the pure color is, if you add white to it and you get lighter, so here's like pure red, if it gets lighter, that's called a tint. And if it gets darker, that is called a shade. Now, yellow is going to have less tints because it's a naturally lighter color. It's a naturally lighter value, and it'll have many more shades. Red is like right in the middle in terms of value. If you took a black and white photo, it would be about 50% gray. So it has, you know, about 49 tints and 49 shades. And then purple, which is violet, which is naturally darker, would have many, many, many more tints and not as many shades. And here you can see a graphic of a more like filled in, this is called the Munsell color space, the Munsell color wheel. So when I think about color, I like to think about it in terms of those dimensions. And then I have that fourth dimension kind of where I split it in half between the warm and the cool. Those are all very useful things to think about when you're dealing with color. There's a technique that an artist, the Impressionists in painting started coming up with this idea, and it was perfected by George Seurat, called visual or optical mixing. And that's when you place two colors next to each other and the viewer's eye does the mixing. So if we take like this fellow's face here, which looks kind of peachy skin color from a distance, if we look at it up close, it's a bunch of intense bright colors. So he's using primary colors and just lightening or darkening them and putting them next together, and that technique was called pointillism. Now, when we're printing, we use the same thing, but we're using cyan, magenta, yellow, and black dots. So here's a painting I did of my old roommate Josh. I printed it out and scanned it, and you can see what my inkjet printer did is it printed a bunch of cyan, magenta, yellow dots and black dots closer or further away from each other with more or less dots, and that recreates the image. But we're using this same idea of visual color mixing. It's just the dots are so small we don't see them. This process was invented by a fellow named Benjamin Henry Day Jr. in 1879, and so we call them the Ben Day dots. This is very important for people who work in any kind of print medium. And this is the CMY color space. So here you'll see if I'm going to make this color, I'm going to have cyan dots of that size, magenta dots of that size, yellow dots of that size, and black dots of that size. They'll combine together like that, and they'll equal that color. Same for this color. You'll see that the magenta dots are much smaller, the yellow dots are much bigger, the black get a little bit darker. Here, the cyan goes down, the magenta gets way bigger, yellow stays the same. So when you're making colors in Photoshop and you're making a raster image, it's kind of like this when it prints out. When you're making a image that's meant to be seen on the screen, or you're doing a vector image, what it's doing is it's putting in a code that's telling the computer what combination of colors, light colors, the red, blue, and green, and then how much light is coming from the screen, basically the illumination, how bright the color should be. And that's, each little dot on your screen is a pixel, and those pixels are being filled in with those colors, and then you're seeing them. It's visual color mixing. Still here, when we zoom in, obviously this section on my screen is still, hundreds and hundreds of pixels. So when you see someone say pixel per inch on a screen, it's how many little like electrodes of light, how many little light bulbs are there in the screen that are reflecting the color back or projecting the color back at you. Are there in 1 inch on the screen? And if you see pixels per inch in print, usually about 300 pixels per inch, that means in any inch of printed material, there's 300 possible dots. And obviously, the more dots you get per inch, the better quality the image is going to be, and we call that resolution. So it's a higher resolution image. This is a very low resolution image. It's one dot is like half an inch. That's a pretty low resolution. I want my screen to be, the 4K Ultra HD, that's like 2400 pixels in an inch. Okay, now basic color schemes are something we can use to help us make decisions in design, what colors go well together. I showed you in Illustrator, they have presets of all of these. You can pick any color and they'll offer you a preset for these and many, many more, which is an awesome tool in Illustrator. We're going to look at a bunch of paintings by the artist Lisa Yuskevich, because she very rigorously applies different color schemes to get effects in her paintings. So it's an easy example of one artist who's got good samples of all of these. Monochromatic is when you choose a single hue, so a single color, and then you just mix black or white to it, and you'll see that it creates an image like this where it's pretty much just saturated in one color. She had a little bit of other color in there, but overall it's monochromatic. And analogous color scheme is if you take the color wheel and you get any like 3 colors that are next to each other, or you could extend that to like 4 colors, but you're taking like a row of colors, usually 3, and you're painting with primarily those. So here you see Lisa Yuskevich is pretty much like over in this section of the color wheel, maybe dipping into the yellow oranges a little bit more, but pretty much over here, and then adding like white into it to get the pinks, and then a little bit going in and adding some cooler colors in there. But that's pretty much an analogous color scheme. A complementary, we already talked about. If you put 2 complementary colors next to each other, like blue and orange, 2 things across the color wheel, red and green, like a red, violet, and a yellow, green, they'll really be an intense color combination. If you tame the colors down, it doesn't have to be as intense, but it's still very striking. So here you have like these light cool greens with these very pink colors there. So that's a good example of a complementary color scheme. A split complement is you'll just take one color and go to its complements, and then you'll use the colors basically on either side of it. Don't use the actual complement. So it's a little bit more sophisticated, and you'll see that here we mostly got all of these like yellow golden colors, and then the red violets and the pinks and the blue violets in the pants and the makeup. So they make these really nice glowing images. Tetradic or rectangular color scheme will basically take two complementary pairs, so a red and a green and an orange and a blue, and use those together. So here you'll see that she's got the reds and the greens and the oranges and the blues. The other nice thing about that is it usually gives you a good warm cool contrast, which is something that's very striking always. You balance like the cool greens against the really warm reds, and that will create a nice deep sense of space and contrast. A square color scheme is pretty much you count every 4 around the color wheel. You could twist that a little bit and compose with that. So here you see that we have like the reds and the greens and the oranges and the like kind of violet-y colors over here in the back, and then these are all more neutral. So that square color scheme is going on back there a little bit better. Triadic, you just do a triangle on the color wheel, and here you'll see that this is a pretty much red, yellow, blue triad, and then the colors have just been desaturated. So you got yellow in the hair, blue in the shirt, red on the leaves there. It's just they're not purely intense. We don't have to always have like these super saturated colors for it to match these color schemes. You could have desaturated yellow, green, desaturated blue, violet, desaturated red, orange, or like here, desaturated yellow, desaturated blue, desaturated red. And then polychromatic is just using a whole bunch of different colors. So here you'll see she's got, just all kinds of different colors, neutral, rainbow colors in the background, all going together. So you don't have to fit into a color scheme. You can apply color however you want, and it will go well. But these color schemes are used by a lot of designers to create palettes. And then achromatic, this one has a little bit of color, but achromatic basically just means black, white, and all of the grays. This is, there's little bits of color in here, but mostly this is a black and white image. There are also effects like optical illusions that happen with color, because our perception of color, like our perception of anything else, is relative to its context. So color is relative to what's around it, what other colors are around it. You'll see here I've got the same reddish color in both, but this one looks more red, this one looks grayer. That's because this is surrounded by a complementary color, a green, and it's cooler, so it makes it look warmer and more red. This is surrounded by a really intense bright red, and so it makes it look darker and duller by contrast. We'll put it into some other situations here. You'll see that this one, because it's surrounded by a darker color, also looks lighter. This one surrounded by a lighter color looks darker, and the intensity of the color changes. Something else you need to think about is the concept of local color. It's a mental construct where we tend to look at an object, and in design it's usually useful, especially in Illustrator, we're working with flat colors. You want to come up with one color that best represents the whole thing. But oftentimes you leave out like effects of situational lighting. So here we've got Scooby-Doo. They're obviously supposed to be in a spooky library, but there's no shading or anything. No one's gotten darker or cooler. It's the same color they would look like if they were outside. On the newer version, you can see they're going in and doing more with shading and changing the colors to make them darker, to make it look like they're inside. But even like his hair and the shirt there probably wouldn't be that bright. But it's just local color is what is the natural color of the thing in daylight, understood by the mind as unaffected by variations in light and dark. Like when you look at a thing and you say it's red, whether it's light or dark out, that's what we mean. Now, there's a weird psychological phenomenon called color constancy. Color constancy means that even as the lighting situation changes, it's changing all of the colors relative to the lighting situation, so you'll still be able to understand the local color. Like here we've got the yellow, red, blue, and green squares, and when we see it in this situation, I can tell yellow, red, green, blue. Same over here, yellow, red, green, blue. as the lighting changes. Now, if I take those colors out and isolate them on their own, it's going to look much different. Like this blue up here, this is the color of it in the light. This is the color of it in the dark. That's that color right there. Here's the yellow. Here's the yellow in the dark. Here's the red in the dark, and the green in the dark. Same over here. There's the blue isolated. There's the yellow. That is that yellow, the red, and the green. Okay, so down here, they definitely don't look like the colors you think they are, but when you put them in a context, your brain maps that color constancy and assumes what the local value is, and it tells you, oh, that's a yellow square. But if I isolated it out and saw that, you'd be like, I don't know, it's some kind of like weird neutral color. Another trick that's really effective, an optical illusion that depends on how your physical system works, that's really effective for graphic design, is the equiluminance. That's anytime you get these weird like electric lines around the edge of things, or where it looks like the color's buzzing. There's not actually lines around here. I made these. That's just a green and a red. That's just I didn't make that one, but that's just a red and a blue. What's happening here is your eyes pick up two different types of information. They pick up information about value, light and dark, and they pick up information about color. Those are picked up separately. The rods in your eye pick up the value information, and the cones pick up the color information. So when it gets sent back to your brain for processing, if we have two colors that are equal value, if I took a black and white photo of these, they'd be the same amount of gray, or very close to the same amount of gray on all of these. So the value sensing part of your brain is saying, well, this is all exactly the same thing. This is all just one gray square. But the color part of your brain is going, oh my God, no, it's like two totally opposite colors. It's red and blue, or it's a really cool color and a really warm color. And so the fight in your own brain between your value sensing system and your color sensing system shows up. You can visibly see the fight at the edges of the objects. Your brain's going, I don't know what's going on here. There's something there, but there's not something there at the same time, and that's where you get the equiluminance effect. So it's very useful for catching people's attention and making posters vibrate. All right, there's so much more to know about color. That's the most basic I can give you. I'm already running over. I try and keep these under 20 minutes. I would suggest taking like the 2D fundamentals class if you want to learn more about color. We spend more time dealing with color in there, but those basics and being able to use those the presets for the color schemes, you know, the analogous, the complementary, split complementary in Photoshop and Illustrator, those should be able to help you. And then, you know, you'll develop your own sense of what works well for colors in your work and what does not work.